Hello. So, let us continue with what we have talked about in the last lecture. In the last lecture, we had talked about how to find out the natural frequencies and mode shapes of a multi-degree of freedom system, and we took an example of a simple 2-degree of freedom system and tried to explain the process using that example. We ended the last lecture by talking about the orthogonality of the mode shapes. So, in this lecture we will continue from the same, and we will talk more about the orthogonality of the mode shapes, and then talk about mass normalization of mode shapes, and see how mass normalization helps in simplifying the expression for orthogonality. So, in the last lecture we had seen that for the example that we had, where R1 was 1.0 and was 1 and minus 0.5. The mass matrix M was M 0 0 to M, and we had seen that R1 transpose into M into R1 was equal to 0. From here onwards, we say that this expression that we have seen for a 2-degree of freedom system hold for any n degree of freedom system, and for a generic n degree of freedom system, this expression can actually be written as R I transpose M into R j is equal to 0 for all I not equal to j. Okay, where M is n cross n, j is n cross 1, and R I transpose is 1 cross n. Okay. So, we have said that earlier that this can also be written in a more generic form as phi transpose into M into phi is going to be a diagonal matrix with all the off diagonal terms 0, where phi is called the modal matrix, which is again n cross n, and this matrix is formed from the mode shapes, and each column of this modal matrix are the mode shapes of the n degree of freedom system. So, this expression of orthogonality is very useful in the later part of analysis of a multi-degree of freedom system. So, one good way to check whether you have found out the mode shapes and the natural frequencies correctly for a given vibrating system is to check for the orthogonality. So, if the orthogonality condition is not satisfied, then there must be some error in evaluating the mode shapes of a system. So, this is also a very good check to see the correctness of the calculations that we have performed. So, let us now move on to mass normalization of mode shapes. So, we have seen that R1, which we had evaluated as 1 1 and R 2 which we have written as 1 and minus 0.5. So, these individual elements of the mode shapes are not unique. I have written it as 1 and 1. I could actually write it as 2 2. I can write it as I can write this as minus 0.5 and minus 0.5. I can also write this as 0.5 and 0.5. Similarly, for this case, I can always write this as 2 and minus 1. I can write this as 4 minus 2. I can write this as minus 1 and 0.5. Okay. So, it is not important for the elements of the mode shapes to have an unique value. What should be unique is the ratio of these two elements of the mode shape. So, the ratio should always be 1. Okay. So, all this possible expression for the mode shapes that I have written has one thing in common, that the ratio of these two is always equal to 1, and so for the second mode shape the ratio of the two element is always equal to 1. So, that is the only uniqueness that we need to have for the mode shapes. Otherwise, if we assume any of this value, all these values are going to satisfy the orthogonality condition, is going to be a solution of the equation that we have been dealing with. So, now in order to bring in some uniqueness or some convention for the expressions of mode shape, so there is a better communication between the people working with on the problem, there should be some method of normalization. I will explain it in another word. I can say that the mode shape is 1 and 1 1. Some other person can say that the first mode shape is minus 0.5 and minus 0.5. So, for a small system this is okay, but for a very large system it will be difficult to communicate between these two persons who are working on the same problem unless we have some method of normalization. One common method of normalization is to make the first element of the mode shape to be 1, and with respect to this first element all other elements are evaluated. So, if I have a n degree of freedom system and my ith mode shape is an n cross 1 vector which has r I 1, r I 2 and so on up to r I n. So, one easy method of normalization is to make this r I 1 equals to 1, and with respect to r I 1 we can evaluate all other elements of the mode shape. So, this is an acceptable form of normalization of mode shape. So, these two mode shapes that we have evaluated are already normalized in that form. We have taken the first element to be 1, the remaining ones are evaluated with respect to the first element. Now, there is another way of normalizing mode shapes which is called the mass normalization of mode shapes. So, let us look into what is meant by mass normalization. So, we have seen that R 1 transpose M R 2 is equal to 0, and R 1 transpose M into R 1 is not going to be equal to 0. So, since 1 is not equal to 2, the two mode shapes is producing this product to be 0. but when I evaluate this integral, this expression, this is not equal to 0. This is going to be some value. But what mass normalization does is that it multiplies the mode shape with a certain factor k, okay, and once I multiply, let me call this new form of mode shape to be okay. Once I multiply this with a certain factor k, I do not know what k is right now. Suppose I multiply the mode shape that I have evaluated and I just multiply with a scalar k and I get a new mode shape which I am calling as Mn. Mn stands for mass normalization. So, what is going to be this factor k? This factor k is such that if I evaluate this product R1 Mn transpose into M into R1 Mn, this should become equal to 1. Okay. So, let me explain this in different words. So, what we are doing is that we have evaluated the mode shapes, we multiply it with a certain scalar term k and get a different form for the same mode shape, such that this mode shape, this new form of the mode shape makes this product R1 Mn transpose into the mass matrix M into R1 Mn equals to 1. Okay. Then this new form of the mode shape R1 Mn is called the mass normalized mode shape. Okay. So, let me explain this with the examples that we are dealing with. So, I have R1 as 1 and 1. So, if I evaluate this product R1 transpose M into R1, I get this as 1 1 M 0 0 2 M, and then I have 1 1. If I evaluate this equation, then I get, so let me just write this again. So, I am trying to evaluate this product. Okay, which is 1 1 okay. So, this is going to be 1 1 and this is going to be M 2 M, which is going to become 3 M. Right. Now, suppose I multiply my R1 by 1 of root over 3 M, and this is going to give me the mass normalized first mode shape. Okay. So, my mass normalized first mode shape is therefore 1 by root over 3 M 1 1, which is 1 by root over 3 M 1 by root over 3 M. Okay. So, this is my mass normalized mode shape. Now, if I take the product of R1 mass normalized into M transpose into R1 mass normalized. Let me see what is going to happen. Okay. So, R1 mass normalized M into R1 mass normalized is going to be 1 by root over 3 m, 1 by root over 3 m into m 0 0 3 2 m into 1 by root over 3 m into 1 by root over 3 m. So, if I evaluate this product, you will see that this is becoming 1. Similarly, let us try to find out the mass normalized second mode shape. So, if I try to find out the mass normalized second mode shape. So, R2 is 1 and minus 0.5. So, if I try to evaluate R2 transpose M into R2, what we get is what we get is 1 minus 0.5 m 0 0 2 m into 1 minus 0.5. So, if we evaluate this, I have 1 minus 0.5 and then I have m and minus 0.5 m. Okay. So, that is going to be m plus 0.25 m. So, if I say that this is m and 0.25 m, then we can see that it is going to be (1.25 m). So, if this is 1 into 2 pi 5 m, then we have this as so if I find out the normalized mode shape, mass normalized mode shape, this is going to be 1 by 1.25 m into R2, which is going to be 1 by root over 1.25 into 1 and minus 0.5. So, this is my mass normalized mode shape 2. Now, we can again evaluate the expression R2 mn into mass matrix M into R2 mn, and that should be equal to 1, okay, where R2 mn is 1 by root over 1.25 m into 1 and minus 0.5. Okay. So, this is going to be the solution for the mass normalized mode shape. So, if my for this particular system, my modal matrix, which is 2 cross 2, is going to be, the first column is going to be the first mode shape. So, it is going to be 1 and 1, and the second column is the second mode shape, which is 1 and minus 0.5. Now, if I write down the mass normalized modal matrix for this particular system, okay, I will have phi which is again going to be 2 cross 2, but it is mass normalized, and that is going to be 1 by root over 3 m, 1 by root over 3 m, and then 1 by root over 1.25 m and minus 0.5 root over 1.25 m. Okay. So, this is the mass normalized modal matrix for this particular system. So, the expression phi transpose m phi is going to be a diagonal matrix with the diagonal terms as 3 m and 1.25 m. Okay. When phi is not a mass normalized matrix, but when for the same system is phi is mass normalized, then this same product is going to look like or an identity matrix I, which is again 2 cross 2, right. So, if I want to summarize what we have done till far is that once we find out the mode shape, the mode shapes are orthogonal to each other with respect to the mass matrix. And when the same product is taken for the same mode shape, then the product is a non-zero value and which is not equal to 1. Now, we can normalize the mode shape in a certain way that the product of R1 transpose M R1 is equal to 1, and similarly R2 transpose M R2 is equal to 1, and so on. Rn transpose M into Rm is equal to 1. Now, this entire thing can be written in a neater form in form of matrix product, where we can write as phi transpose M phi is equal to an identity matrix provided phi is mass normalized. If phi is not mass normalized, then it will become a diagonal matrix, but the diagonal terms are not going to be 1, but certain other values. So, this expression for orthogonality of mode shape and mass normalization of mode shapes are very useful for the later analysis of the vibratory system. So, we will see that this expression can be used very efficiently to simplify certain equations of motion of a multi-degree of freedom system, and thereby making the solution of those equations of motion very simpler. So, the takeaway of this whole part of this lecture can be said that if I find out the mass normalized mode shape of any n degree of freedom system and then derive this product, this is going to be an identity matrix. If they are not mass normalized, if I don't mass normalize them, if I just take the any modal matrix having any number of having the any form of the eigenvectors, then this is not going to be I, but instead a diagonal matrix having the diagonal terms, certain non-zero diagonal terms and all the off diagonal terms being 0. So, this is going to be used in later part of the lecture to solve the other different classes of problem. So, in the next lecture, we will talk about how this orthogonality of the mode shapes can be proved for any arbitrary multi-degree of freedom system, and then we will solve the problem of finding out the free vibration response of a multi-degree of freedom system. Thank you.